In this module, we're going to meet several new shapes of graph. Each of them represents a different type of quadratic equation, and all of them come from one and the same geometric figure, but only when we look at it in quite different ways. Imagine a large, double-ended ice cream cone, without any ice cream, sadly, and think about what happens when we take a flat slice through it. A cut like this is called a section. Notice the shape you're left with along the edge of the cone. Here, a perfectly horizontal section gives us our old friend, the circle. Now, if we tilt the knife a little, we get a sort of flattened circle called an ellipse. Not really a circle at all, of course. That's why it has a different name. And if we tilt our slice or section a little further and make it parallel to one edge of the cone, we get something else you've seen before, a parabola. Finally, if we take a precisely vertical cut, we get a curve that has two separate parts, a hyperbola. These four different shapes, circle, ellipse, parabola, hyperbola, are called cone sections or conic sections. Each of them comes from a different way of making a flat slice or section through a cone. Since we have a separate module on circles, we'll just give them a glance here and then concentrate on the other three kinds of sections. You remember that we got our algebra equation for a circle by looking at all points which were a constant distance r from the center AB. Then we used the distance formula. Okay, now we're going to get formulas for the other conic sections in a similar way. First, the parabola. In this case, we have a fixed point called the focus and a fixed line called the directrix. And we look for points that are an equal distance from the focus point and from the nearest point on the line, the directrix. We've marked some of those points here. When you join all such points together with a nice smooth curve, you get this parabola. Great. But now that we have it, what is its equation going to be? Let's find out. First, we give some letters to the focus point and to the directrix line. Then we can work out those two distances which our description said had to be equal. The first one is an easy horizontal distance, and the second one uses our distance formula. Setting them equal gives us our equation. Now you can either simplify that equation yourself, or you can look it up in your textbook. But the final shape looks like this. Remember it. It's one of the standard equations for a parabola. What does that mean, one of the standard equations for a parabola? It means that there are several other possibilities, like these. We put in an extra negative sign, and we get a parabola opening in the opposite direction. Or we interchange x and y and get a third possibility. Then another negative sign gives us a fourth position for the same parabola. There are also many other parabolas which we won't look at in this course, but you should be able to recognize at least these four basic shapes. And if you look closely, you may be able to recognize a real live parabola when you see one, in the parking lot. The headlights on your car use a property of parabolas to produce beams of light that are exactly parallel. Our next shape, an ellipse. How do we define it? By using two fixed points instead of one. To get an ellipse, we take all points where the sum of their two distances to the two focus points is a constant. Here are some examples. All of these points joined together by a nice smooth curve give us our ellipse. We have the shape. Now, what about the equation? The first thing we do is assign letters to the two focus points, just as we did for the parabola. Then we use the distance formula twice and throw in a little geometry to get an equation for the sum of the distances. Once again, you can simplify it, or you can look it up in your book. But once again, what you need to remember is the final shape, one of the standard equations for the ellipse. Notice the positive and negative c's from the two focus points have disappeared. This is the ellipse where A is larger than B. The other possibility, A smaller than B, gives us a similar shape, but its longer direction, called the major axis, is along the y or vertical axis. Where would you look for an ellipse in the real world? Look up and out, because space is full of ellipses. Our own Earth moves in a giant ellipse with the sun sitting at one focus point. Our final shape is a set of twins created by that odd vertical section through both of our cones, the hyperbola. When we go to make a hyperbola, we'll still have two fixed points, but in this case we subtract distances instead of adding them. The distance to one focus minus the distance to the other is equal in every case. We mark the points and find that our nice smooth curve comes in two separate parts. We still have the same special points we did before, the two focus points, vertex and center, and we can get an equation describing the distances. We introduce A into the equation just as we did before, but this time A doesn't show up on the picture at all. If you want all the details about that, you can look them up in your book, but don't worry about it. And when we do the algebra to simplify the equation, check your book again, we get an equation that's almost the same as the one for an ellipse. The negative sign in the middle is the only difference. Notice that this hyperbola lines up along the y-axis. We could have the same hyperbola lined up along the horizontal or x-axis instead. How? By doing our subtracting in the opposite direction, or, same thing, by switching the order of terms. What about the real world? Are there any hyperbolas out there? The next time you pass a power plant, take a close look at one of those big cooling towers. But in that case, you'll want to be sure that the two curves are upright. They don't work too well the other way. Well, that's quite a collection of new equations. Here they are, all at once. You'll want to be able to recognize them when you see them, and use them to sketch the graphs of equations like this. It's a quadratic equation, so it ought to be one of our new shapes. Which one? I know it's not a circle because the two coefficients are different. The plus sign tells me that it could be an ellipse, but for that I'm going to need a 1 on the right. So I divide by 36 and get a 1 on the right. Now I have it in the standard shape. A is smaller than B. So we end up with a vertical ellipse like this. That wasn't too bad. The trick is to recognize the shape of the equation and then write it in one of the standard forms. Here's one for you to try. And remember what I just said. The trick is to recognize the shape of the equation and then write it in one of the standard forms. Come back as soon as you have your answer. I see an equation with one square term and one linear term. That seems to suggest a parabola, so I rewrite it in standard form like this. And when I graph my parabola, it looks like this, with focus at -2, 0. If you want to try some more examples or check some of the proofs for the equations, just look in your book. You'll find it all there. One final idea before you go. There are two very special straight lines which are related to a hyperbola in the way that you see here. They are called asymptotes. The equation for the asymptotes is exactly the same as the equation for the hyperbola, except for one thing. Change the 1 to a 0, and you've got it. How does that work? Like this. We can factor the asymptote equation, and when we do, we come up with two straight lines. So now you know. You'll learn lots more about conic sections in your next algebra course, and also in calculus. But for now, you'll just want to be able to recognize which type of equation is which, and be able to sketch the right graph for the right equation. Good luck!